Welcome to this coding walkthrough. Today, we will be tackling problem number 227, Basic Calculator 2. This problem focuses on evaluating mathematical expressions with operators like addition, subtraction, multiplication, and division. Stick around as we break it down step by step and explore efficient ways to solve it. This problem asks us to evaluate a mathematical expression provided as a string. The string will contain non-negative integers, along with the operators plus, dash, asterisk, and forward slash, as well as spaces that need to be ignored. One important point is that division must truncate towards 0, meaning the result should be rounded towards 0 instead of following standard rounding rules. Additionally, we are not allowed to use built-in functions like eval, so we need to implement the logic to parse and calculate the expression ourselves. The input is guaranteed to be a valid mathematical expression, and its length can go up to 300,000 characters. Finally, our output should be the integer result of evaluating the provided expression. For example, if the input string is 3 plus 2 asterisk 2, the output should be 7. This is because we first perform the multiplication, 2 by 2, which equals 4. Then, we add this result to 3, giving us a final result of 7. In another example, the input string 3 halves would output 1. Here, the division 3/2 truncates towards 0, which means instead of getting a decimal result like 1.5, we simply return the integer part, which is 1. Handling spaces in these examples is also crucial, as they are ignored during evaluation. Now consider the input string 3 plus 5 halves. The correct output here is 5. First, we handle the division operation, 5/2, which equals 2 when truncated towards 0. Then, we add this result to 3, giving us the final answer of 5. The problem also specifies several constraints, such as ensuring all intermediate results fit within the range of a 32-bit signed integer. This guarantees that we won't encounter overflow issues during computation. Additionally, the input string will always include at least one digit, ensuring it represents a valid expression. There are a few edge cases to keep in mind when solving this problem. First, the input expression may have spaces in arbitrary positions, such as around operators or numbers, and these must be ignored during evaluation. Second, the input could consist of just a single number, like 42 foot, in which case the output should simply be that number. Third, when performing division with negative numbers, the result must truncate towards 0, so -3 halves should evaluate to -1. Finally, we need to respect the order of operations, meaning that multiplication and division take precedence over addition and subtraction. This ensures the expression is evaluated correctly, regardless of the order in which the operators appear. To solve the basic calculator 2 problem, we need to evaluate a string containing mathematical expressions with non-negative integers and the operators plus, dash, asterisk, and forward slash. Importantly, we must respect operator precedence, meaning multiplication and division take priority over addition and subtraction. One approach we considered is a brute force 2-pass solution. In this method, we first parse the string to handle all multiplication and division operations, which have higher precedence. Then, we iterate again to process addition and subtraction. While this simplifies the problem by separating precedence levels, it has challenges. Specifically, it requires extra memory to store intermediate results and involves multiple passes over the string, making it less efficient for large inputs. Although its time complexity is O(n), the multipass nature introduces inefficiencies compared to other methods we will discuss next. Another approach is single-pass stack-based evaluation. This method uses a stack to maintain operator precedence dynamically while iterating through the string. The idea is to evaluate multiplication and division immediately because they have higher precedence, while deferring addition and subtraction by pushing partial results onto the stack. To do this, we keep track of the current number and the last operator. For asterisk and forward slash, we directly compute the result with the last number in the stack. For plus and dash, we push the number with the appropriate sign onto the stack. At the end, we sum all the values in the stack to get the final result. This approach leverages the stack to simplify precedence handling without requiring multiple passes or transformations. While it has the same O(n) time complexity as the brute force approach, it is more efficient due to its single-pass nature and has an O(n) space complexity to store intermediate results. Another approach we considered is converting the infix expression into postfix notation, or reverse Polish notation, and then evaluating it. While postfix eliminates the need for parentheses and explicitly enforces precedence, the conversion process is complex and adds unnecessary overhead for this problem. Despite its elegance, this approach is overkill given the simpler alternatives available. Ultimately, we chose the single-pass stack-based evaluation approach for its balance of simplicity and efficiency. The key insight is recognizing that multiplication and division must be computed immediately, while addition and subtraction can be deferred. This avoids multiple passes and eliminates the need for unnecessary transformations like infix to postfix conversion. To implement this, we iterate through the string, parsing numbers while skipping spaces. Based on the last operator, we decide whether to push the current number onto the stack or compute it with the top of the stack ** and /. At the end of the iteration, we sum all values in the stack to compute the final result. This approach dynamically enforces operator precedence and avoids extra overhead, making it the most suitable solution for this problem. The time complexity of this approach is O(n), because we traverse the string once. The space complexity is also O(n), due to the stack, which stores intermediate results. Other approaches, while viable, were not chosen due to their drawbacks. The brute force method introduces inefficiencies with multiple passes over the string, requiring extra memory for intermediate results. On the other hand, the infix to postfix approach, while elegant, is unnecessarily complex for this problem. The single-pass stack-based evaluation strikes the best balance, providing a straightforward implementation with minimal overhead while ensuring correctness. To solve this problem, we start by breaking the expression evaluation into clear steps. First, we initialize a stack to manage intermediate results, which helps us handle operator precedence naturally. Alongside this, we use a variable current_number to construct multi-digit numbers while parsing the string, and another variable current_ operator to keep track of the last operator encountered, initially set to plus. Then, we traverse the expression character by character. When we encounter a digit, we update current_number by shifting its value left and adding the new digit. For instance, if the current number is 3 and the next digit is 5, current_number becomes 35. This ensures we can handle multi-digit values seamlessly. When an operator or the end of the string is reached, we process the number accumulated so far based on the last operator stored. For example, if the operator is plus, we add the number to the stack, preparing it for later computation. If the last operator is dash, we push the negative of current_number onto the stack. For multiplication or division, we first pop the top value from the stack and perform the respective operation with current_number. The result is then pushed back onto the stack. For division, it's important to ensure truncation towards 0, which Python handles for positive numbers using integer division. After processing the operator, we reset current_number to 0 and update current_operator to the current character. Once the traversal is complete, the stack contains all the intermediate results, including positive and negative values resulting from addition and subtraction. To compute the final result, we simply sum all the values in the stack. This approach ensures that operator precedence is respected, and the calculation is both accurate and efficient. This algorithm has several important insights. First, operator precedence is managed naturally using the stack. Multiplication and division are executed immediately, while addition and subtraction are deferred, as their results are stored in the stack. Next, integer division must truncate towards 0 to handle both positive and negative numbers correctly. Python's // operator works for positives, but for negatives, explicit handling may be needed. Additionally, the algorithm achieves O(n) time complexity by traversing the string only once and processing operators as they are encountered. Edge cases such as spaces in the input are handled by simply ignoring them during traversal. Consecutive operators are processed correctly by always applying the previous operator before updating to the current one. Finally, division by 0 is avoided by adhering to input constraints that prevent such scenarios. Now, let's look at the data structures and variables used. The stack is crucial as it stores intermediate results for addition and subtraction, deferring their computation until higher precedence operations are resolved. This makes it ideal for handling mixed operators. The current underscore number variable is used to accumulate multi-digit numbers during parsing, while current underscore operator tracks the previously encountered operator to decide how to process the current number. To illustrate, consider the example input 3 plus 2 asterisk 2. We will step through the algorithm to see how these components work together to compute the result. We start by initializing the stack as empty, current underscore number as 0, and current underscore operator as plus. As we traverse the string, we encounter the digit 3, so we update current underscore number to 3. When we reach the plus operator, we process the current operator, which is also plus. This means we push 3 onto the stack, reset current underscore number, and update current underscore operator to plus. Next, we see the digit 2, so we set current underscore number to 2. When we encounter the asterisk operator, we process the previous plus, pushing 2 onto the stack, resetting current underscore number, and updating current underscore operator to asterisk. Finally, we see another 2 and update current underscore number to 2. At the end of the string, we process the asterisk operator. This involves popping 2 from the stack, multiplying it by 2, and pushing the result, 4, back onto the stack. The stack now contains 3, 4, and summing these values gives the result, 7. The algorithm's time complexity is O(n) due to the single traversal, and its space complexity is O(n) in the worst case, where all numbers are pushed onto the stack. This solution evaluates a string mathematical expression containing integers and operators plus, dash, asterisk, and forward slash. The algorithm relies on a stack to handle operator precedence and evaluate the expression in a single pass. Step-by-step explanation. 1. Initialization. A stack is used to store intermediate results. Current underscore number accumulates multi-digit numbers from the string. Current underscore operator tracks the last encountered operator, starting with plus as the default. 2. Iterating through the expression. We loop through each character in the input string s. If the character is a digit, we build the number by multiplying current underscore number by 10 and adding the digit. 3. Handling operators and end of string. When encountering an operator or reaching the end of the string, evaluate the previous operator, current underscore operator, using the current underscore number. For plus and dash, push current underscore number, or its negation 4 dash, onto the stack. For asterisk and forward slash, pop the last number from the stack, apply the operation with current underscore number, and push the result back onto the stack. Update current underscore operator to the current character and reset current underscore number to 0. 4. Final calculation. After processing all characters, the result is the sum of all numbers in the stack. Key edge cases. Spaces, ignored during processing since the loop handles only digits and operators. Division, uses integer division, truncating towards 0, to match problem requirements. Single numbers, returns the number itself if no operators are present. This approach ensures efficient and correct evaluation of the expression in O(n) time, where n is the length of the string. It avoids nested iterations by using the stack to handle precedence directly. Here, we start by importing the necessary utilities and defining our solution class with the calculate method. This method takes a string s as input, which represents the mathematical expression to evaluate. We initialize a stack to handle intermediate results, a variable current number to build multi-digit numbers as we parse the string, and current operator to keep track of the last operator encountered, starting with plus. Then, we loop through each character in the string. If the character is a digit, we update current number by multiplying the existing value by 10 and adding the numeric value of the current character. This allows us to handle numbers of any length. Now, if the character is not a digit and not a space, or we've reached the end of the string, we process the current number based on the last operator. For addition, we push the number onto the stack. For subtraction, we push its negative. For multiplication and division, we pop the top of the stack, perform the operation with the current number, and push the result back onto the stack. After processing, we reset current number to 0 and update current operator to the current character. Next, we handle the final part of the calculation. After the loop, all intermediate results are stored in the stack. To compute the final result, we initialize a variable result to 0 and iterate through the stack, summing up all the values by popping them one by one. This works because the stack contains the results of all the operations performed during parsing, with addition and subtraction already handled by the signs of the numbers. Finally, we return the accumulated result, which represents the evaluated value of the input expression. This approach ensures that all operations are performed in the correct order, adhering to the rules of operator precedence without the need for additional data structures. In this example, we are evaluating the expression 3 plus 2 asterisk 2. To start, we initialize the necessary variables, an empty stack to store intermediate results, a current underscore number set to 0 to build numbers from the input string, and a current underscore operator initialized to plus. In the first iteration, the character is 3, which is a digit. We update current underscore number by multiplying the current value by 10 and adding the digit, resulting in current underscore number equals 3. In the second iteration, the character is plus, which is an operator. At this point, we process the previous operator, which is plus. Since the operator is addition, we append current underscore number, which is 3, to the stack. The stack now contains 3. We then reset current underscore number to 0 and update the current underscore operator to plus. In the third iteration, the character is 2, another digit. We update current underscore number again as before, resulting in current underscore number equals 2. Now, in the fourth iteration, the character is asterisk, an operator. We process the previous operator, which is plus. This means we append current underscore number, which is 2, to the stack. The stack now looks like 3, 2. Next, we reset current underscore number to 0 and update the current underscore operator to asterisk. In the fifth iteration, the character is 2, a digit. We update current underscore number to 2. Once we reach the end of the string, we process the last operator, which is asterisk. To do this, we pop the top of the stack, which is 2, multiply it by current underscore number, also 2, resulting in 4. We then push this result back onto the stack, so the stack becomes 3, 4. Finally, to compute the result, we sum the stack, which gives 3 plus 4 is equal to 7. Therefore, the output of this expression is 7. In this second example, we evaluate the expression 3 halves. We start by initializing the same variables, an empty stack, current underscore number equals 0, and current underscore operator equals plus. In the first iteration, the character is 3, a digit. We update current underscore number to 3 by multiplying by 10 and adding the digit. In the second iteration, the character is /, an operator. At this point, we process the previous operator, which is plus. This means we append current underscore number, which is 3, to the stack. The stack now contains 3. We then reset current underscore number to 0 and update the current underscore operator to /. In the third iteration, the character is 2, another digit. We update current underscore number to 2. At the end of the string, we process the last operator, which is /. To do this, we pop the top of the stack, which is 3, and divide it by current underscore number, which is 2. The result is 1.5, but since we are performing integer division, we take the floor of the result, which is 1. We then push this result back onto the stack, so the stack becomes 1. Finally, to compute the result, we sum the stack, which gives 1. Therefore, the output of this expression is 1. Next, we consider a more complex example, 14-3 2. Once again, we initialize the variables, an empty stack, current underscore number equals 0, and current underscore operator equals plus. In the first iteration, the character is 1, a digit. We update current underscore number to 1. In the second iteration, the character is 4, another digit. We update current underscore number again, resulting in 14. In the third iteration, the character is dash, an operator. We process the previous operator, which is plus. This means we append current underscore number, which is 14, to the stack. The stack now contains 14. We then reset current underscore number to 0 and update the current underscore operator to dash. In the fourth iteration, the character is 3, a digit. We update current underscore number to 3. In the fifth iteration, the character is asterisk, an operator. At this point, we process the previous operator, which is dash. This means we append the negative of current underscore number, which is -3, to the stack. The stack now looks like 14 minus 3. We then reset current underscore number to 0 and update the current underscore operator to asterisk. In the sixth iteration, the character is 2, another digit. We update current underscore number to 2. At the end of the string, we process the final operator, which is asterisk. To do this, we pop the top of the stack, which is -3, and multiply it by current underscore number, which is 2. This gives -6, and we push this result back onto the stack. The stack now becomes 14 minus 6. Finally, to compute the result, we sum the stack, which gives 14 plus -6 equals 8. Therefore, the output of this expression is 8. The time complexity of this algorithm is determined by how it processes the input string. Since the algorithm examines each character of the input exactly once, it operates in O(n) time, where n is the length of the string. First, let's consider digit parsing. Every time the algorithm encounters a digit, it updates the current underscore number variable, and this is done in constant time, O(1). Over the entire string, this process contributes O(n), because there are n characters, and each is processed individually. Next, when the algorithm encounters an operator or reaches the end of the string, it evaluates the current underscore number using the last current underscore operator. Actions like appending numbers to the stack or performing arithmetic operations, such as addition or division, are also constant time operations, O(1). Since this happens at most n times, given that there are at most n operators, this step also contributes O(n) overall. After the main loop finishes processing the string, the algorithm computes the sum of all elements in the stack. Summing the stack involves iterating through its elements, which takes k time, where k is the number of elements in the stack. In the worst-case scenario, each digit could correspond to a separate entry in the stack, meaning k equals n. Therefore, this step contributes O(n) as well. When we combine all these steps, digit parsing, operator handling, and summing the stack, the total time complexity becomes O(n) plus O(n) plus O(n), which simplifies to O(n). Now, looking at space complexity, the primary contributor is the stack. In the worst case, where each number or intermediate result is stored as a separate entry, the stack can hold up to n elements. Thus, the space complexity of the stack is O(n). In addition to the stack, the algorithm uses a few auxiliary variables such as current underscore number, current underscore operator, and some loop variables. These variables take up a constant amount of space, O(1), regardless of the size of the input. Therefore, the overall space complexity of the algorithm is determined by the stack, which is O(n). Comparing this approach to a naive solution, a brute force method might involve multiple passes over the string, such as handling multiplication and division in one pass, and then addition and subtraction in another. This would result in a time complexity of O(n squared, because of repeated scanning and operations on the string. By contrast, the current solution is optimized to handle all operations in a single pass using a stack, achieving an efficient O(n) time complexity. The algorithm performs consistently across different scenarios. In the best case, if the input string contains only a single number, it is processed in O(n) time with minimal stack usage. For the average case, where the input is a typical arithmetic expression, the algorithm still processes each character once and uses a linear amount of stack space, maintaining O(n) time and space complexity. In the worst case, such as an input containing many numbers and operators, like 1 plus 2 plus 3 plus n, the algorithm continues to operate in O(n) time, with O(n) space required for the stack. To summarize, the algorithm's time complexity is O(n), since each character is processed exactly once, and stack operations are linear in size. Similarly, the space complexity remains O(n), because the stack's size depends on the number of elements it holds, which is at most n. When solving this problem, there are a few common mistakes to be aware of. First, ignoring operator precedence can lead to incorrect results. For example, evaluating an expression like 3 plus 5 by 2 strictly left to right without recognizing that multiplication has higher precedence than addition will produce the wrong answer. To avoid this, you can use a stack to handle intermediate results and ensure that operators are applied in the correct order. Another issue is not handling whitespaces properly. Expressions may include extra spaces, such as 3 plus 5 by 2, and failing to account for them could result in parsing errors. The solution here is to either trim spaces from the input or skip them as you iterate through the expression. Finally, integer division errors can occur if you use regular division instead of integer division. For instance, in Python, using the slash operator produces a float, which might not meet the problem's requirements. Always ensure you're using integer division, like the double slash operator in Python, to maintain correctness. Another common mistake is not handling negative results properly. This often happens when subtracting or dividing values, particularly when using a stack. For example, if you encounter an expression like -3*2 or 5/-2, forgetting to account for the signs can lead to incorrect outcomes. The fix here is to carefully apply the operator to the most recent value in the stack while preserving the correct sign. Additionally, stack mismanagement is a frequent source of errors. Misplacing values, applying operations in the wrong order, or popping the wrong elements during multiplication or division can all result in incorrect calculations. To avoid this, it's crucial to carefully manage how values are pushed to and popped from the stack, and to thoroughly test your solution with edge cases to ensure it behaves as expected. This problem is a great opportunity to demonstrate your ability to simulate computational processes during interviews. One key aspect interviewers look for is your ability to systematically handle operator precedence. Additionally, you should be prepared to address edge cases, such as expressions containing only a single number like 3, multiple spaces like 3 plus 5*2, or even very large inputs that may test the efficiency of your solution. Another common discussion point is optimization. While the stack-based approach is widely accepted, interviewers might challenge you to explore whether a single-pass solution is possible. If they do, it's a good idea to discuss the trade-offs between readability and complexity, as a single-pass implementation may be more efficient but harder to understand. The concepts in this problem are closely related to several other problems on LeetCode. For instance, Basic Calculator 2 is part of a progression of calculator problems. The original Basic Calculator problem, LeetCode 2.24, introduces parentheses and requires you to handle nested expressions. Then, there's Basic Calculator 3, which further extends the problem by including both parentheses and additional operators. Another related problem is Evaluate Reverse Polish Notation, LeetCode 150. While it also relies on a stack-based approach, it uses postfix notation instead of infix, which presents a different but related set of challenges. Exploring these problems can help you strengthen your understanding of similar computational techniques and patterns. There are several alternative approaches to solving this problem, each with its own trade-offs. The two-pass approach involves evaluating multiplication and division in the first pass, then handling addition and subtraction in the second pass. While this method is straightforward and easier to implement, it's less efficient for very large inputs. A more efficient option is the single-pass approach using a stack, where you process the expression in one iteration and maintain intermediate results in the stack. This method has a time complexity of O(n), making it faster, though slightly more complex to implement. Finally, you can use recursive parsing, which is particularly helpful for problems that involve nested expressions, such as Basic Calculator 3. Recursive parsing is elegant and handles parentheses well, but it may consume more memory and take longer to execute due to its recursive nature. Each approach has its strengths and weaknesses, so it's important to consider the requirements of the problem and choose appropriately. Great job on completing this walkthrough. To summarize, we tackled the problem by leveraging a stack to handle operator precedence, ensuring efficient evaluation of the expression. We hope this tutorial helped you understand the concepts and boosted your confidence for similar problems. Don't forget to like, subscribe, and share this video. See you in the next one. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!